In the previous video, we calculated all these numbers, most of which we don't even need to worry about. But the stuff that we've highlighted gives us different regions on the titration curve in terms of amount of base added. And now we want to calculate our predicted pH values. So in order to do this, and thank you for the miracle of modern paper, I can continue on with my work from the previous video, which was part 1, the basic stoichiometry. And now we're going to look at part 2, which is going to be for a strong acid. All right. Anyway, we're going to use these numbers. It doesn't really matter which side we use. The strong acid we're going to work with, it says in this case your acid HA. The acid we're going to work with here is going to be HI, which is a strong binary acid. All right. And what we're looking for here is what happens when we have these amounts. How's the pH going to change based on concentration? So we need to set up an aqueous dissociation equation for that. HI, that's aqueous, plus H2O, it's going to give us H3O plus and I minus. Both of those are aqueous. All right. Now, just to use this space up here, I've got a Ka value for this that's large. It's a strong acid, and that is H3O plus and I minus over HA. We won't need that equation, but that's what it would look like when we set it up. So we are going to do ice here. Take note, I didn't do ice there. In fact, I wrote stoichiometry, 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 stoichiometry. But I am going to do my ice problems in parallel to that, all right? I don't really feel like writing ice all the way down, but I guess I could. All right, and there we have ice all the way down. Now, if you're planning ahead, we don't need to do this, all right? So don't think you've caught me unaware. I just want to show it at least once, and there's not really any clear color coding to what was about to take place here. We're starting out with 0.20 molar. In fact, if I set this up here, it'll look a little better. 0.20 molar HI. We've got nothing to worry about for the H2O, 10 to the minus 7th for the H3O plus, and 0 for the I minus, because we haven't made any yet, right? In this particular case, then, since it is strong, our Ka value is large, we're going to lose all of it. And we're going to gain 0.20 on the other side and gain 0.20 on the other side, right? And so we end up with 0 and 0.20, 0.20, which makes our pH very easy to calculate, because it's just the negative log concentration H3O plus. pH is going to be the negative log concentration H3O plus. And in this case, our pH is the negative log of 0.2, and that is 0.699. All right, so our first pH there is 0.699. Now, since it's a strong acid and it dissociates completely, all we got to do is look at these numbers, and that's what our H3O plus is going to be. So if you look right here, our initial concentration is what we're going to end up with right there. So if this is 0.15, in fact, I'll just write 0.15, 0.05, all right? Luckily, I highlighted these because I already got lost. And then we've got, in this particular case, 0 and 0.20. And we'll have to deal with a different situation once we get there. But for now, these numbers that I'm carrying over, in fact, it couldn't hurt, although it could totally hurt, if I declare that these numbers got carried over from our stoichiometry to our ice. All right, now, skipping all that ice, everything that we had dissociated, we're going to end up with right here, 0.15, right here, 0.10, and right here, 0.05. And then this is going to give us 0.20 still, 0.20, 0.20. In fact, that 0.20 is going to carry all the way down. Since this is a 0, we will get a 0 right here, and we're still going to get 0.20 right there. All right, got those lined up. This means the numbers we're actually interested in for the dissociation calculation, or sorry, for the pH calculation, are this number, this number, this number, and then that number I'm not looking at because that solution is neutral. And so we just run down here and do these pH calculations. This is going to be the negative log of 0.15. This is going to be the negative log of 0.10, negative log 0.05, and then this, the pH is going to be 7. Alright, and if you look at our titration curve here, in the beginning, in these steps right here, we have excess strong acid, and then this I minus, or NaI depending on your opinion, is a neutral salt. So once we've used up all that excess acid, and we just have neutral salt there, it's going to be neutral pH 7. Alright, so I guess I could fill these in a little bit more, but for right now, let's write these numbers down. That pH, there's my red marker, 0.824, 1.000, I don't know, I had to look at that one, 1.301, and then we've got that one as pH 7. So up until this point, excess acid, strong acid dissociates, we get those pHs right there. Then it's pH 7, and all of a sudden we have a situation where it becomes basic, and the calculations change a little bit. In this step right here, I guess it would be better to mention something that when I cut my corners isn't obvious to see, and that is that right there we have 10 to the minus 7th. We're assuming 10 to the minus 7th to begin with, so if we put our 10 to the minus 7th right there, we do end up with 10 to the minus 7th right there when there's a change of 0. I guess that might be a little easier to see. Now let's take a look at these base calculations, because once we get to here, something different happens. Now all of a sudden we don't have any of this HI anymore. We have H3O plus, but it's significantly less than our excess OH minus, which is 0.05, or in this case 0.05 molar, since I chose 1 liter. So the pH all of a sudden becomes exclusively based on that. We don't have an H plus. We could get an H plus a couple different ways. We could say, I'm having marker color crisis here. We could say at 25 degrees Celsius, pH plus POH equals 14. All right, that's one way to handle it. Alternately, you could say that concentration H3O plus is going to be KW over concentration OH minus, or whatever you want. And I think the way I'll handle it right here to be time efficient is to just say that our pH for these calculations is going to be 14 minus the POH. So I'll use this right here. It doesn't really matter how you do it. In this particular case, that is the negative log H3O or OH minus. So pH is going to be 14 minus the negative log concentration OH minus. All right. And for these calculations, we've got in this one right here 0.05. So 14 minus, well, plus the log 0.05, and that gets you 12.699. This is 14 plus the log of 0.10, and that gives you 13.000. This one ends up 14 plus the log of 0.15, and while we're at it, 14 plus the log of 0.20, and that's 13.176 and 13.301 for our pH. All right, and again, each of these was an addition of 0.05 moles of that OH minus. So for these right here, we had excess OH minus. And so we calculated it that way. And a quick glance at how these numbers match up to our picture. We have 0.699 for a pH, jumps up, jumps up, jumps up. Huge jump as we neutralize it and then start getting into excess base. And then we have this logarithmic function as we're just dealing with continued excess base. So that is our calculation for a strong acid, And it's going to be a little different for a weak acid. What we're going to have in common is 0.2, 0.15, 0.10, 0.05, 0, 0.05, 10, 0.15. Those are numbers that came directly from here, right? Well, let's put it like that. Those are numbers that came directly from there. Now, once we have both sides of this, though, like that, we're going to have a buffer system. And since it's a weak acid, it's a little more work.